Hello everyone. Today we are going to study the fifth unit, that is slope and deflections of the beams. Today we are going to study and find out how we are going to find out the slope of the beam and the deflections in the beams. Okay, and how to calculate those deflections and slopes in the beams. It becomes very important to identify the deflections and the slope in the beams because when we are uh, trying to look at the serviceable limit, that is when the structure is under the service, means it is under the use, that time the loading is been there will be a loading, right? Always there will be a loading on the building, because we are going to use the building, means there is going to be a change of the loads, transfer of the loads at different points. There will be different loadings. So on depending upon those loadings, okay, depending upon those loadings, the the beam will try to deflect, try to deform. Okay, that deformation which occurs in a curved fashion, okay, along its longitudinal axis, okay, that deformation is called as deflection. Okay, we'll try to find out through the technical terms. Okay, here, if a beam carries a uniformly distributed load or a point load, the beam is deflected from its original position. Okay, this is called as deflection. When the beam is um, loaded with an any type of load, that is UDL or a point load, then there might be a deformation along its longitudinal axis, along its lengthwise, okay, that that type of deformation is called as deflection. Okay, you can see here in this the first picture, right? You can see in this first picture that the beam is loaded here at the point C, right? then then due to that loading, there is a deflection of this beam, right? Okay. So when how much is that deflection, that is what we want to find out. Okay, when we load, what will be that deflection, that we want to find out. Okay, the beam should be strong enough to resist these loads depending upon its cross section and bending moment. This resistance of the beam depends upon the cross section, that is the width and the depth of the beam, length of the beam, not length of the beam, but yeah, it depends upon length of the beam, because the length, as the length increases, the depth and the loading increases, the deflection also goes on increasing as the span increases. Okay, so it is very important, cross section, the length and the bending moment, how much bending moment is been countered or is coming over the beam, that is very much important. Okay, beam should not be more than the permissible limit. This is an important thing. Okay, what we want to say is there is a certain limit to the beam depending upon its span of the beam. Okay, depending upon its length of the beam, okay, that is the effective length. Depending upon that, we have to fix the value of deflection for that type of beam, that length of beam. So what is that formula, how to calculate that permissible limit? That is uh, as per the Indian standard, it is limit is span by 325. If there is a span of 4 meters and you divide it by 325, or if you can do, if you want the deflection in mm, we always calculate the deflection in mm, so we'll try to put the length also in mm. So if 4000 is your 4000 mm is the span, divided by 325, whatever the value you get, the deflection should not occur more than that value. That is what is a permissible limit is. Excess of loading in the beam, excess of deflection in the beam of the building leads to crack in the plaster of the walls and the ceilings. You might have seen there might be cracks being developed on the walls or on the beams, right? So these are due to the deflections. Due to the deflections, it is trying to deform, and it is putting the excess pressure over the walls. Due to this excess pressure on the walls are been pushed downwards, they are in compression, so there is a crack formed on the walls and the plaster of the walls. Okay, and we will try to find out the new terms in this subject. Okay, when a straight beam is loaded on the longitudinal axis of the beam becomes curve, right? As you saw in the first figure, that when you load the beam, straight beam, when you load a point load or any radial load, it deforms. That deform will be in the curved fashion or curved shape. Okay, so that curved shape is called as elastic curve. when you when you apply the load and there is a curve, okay, that curve is called as elastic curve, right? The angle made by the tangent drawn to the deflection of the curve with the horizontal axis of the beam is called slope. This is also important because we want to find by what degree this deflection is occurring. So to calculate the degree, we have to find out the slope of that curve. Okay, means what? I'll tell you what it is. This is your beam and this is your deflection, right? So the deflection will be what? This is your curvature, this is your elastic curve. Whatever I have shown, that is your elastic curve. Because due to loading it is bending, there is a deformation. So due to that deformation, there is a elastic curve. When you draw a tangent to this elastic curve like this, right? And when you draw the tangent to that elastic curve, to that tangent draw a horizontal line, right, to that elastic curve like this, and the angle made by the horizontal line with the tangent, that is theta, is called as slope. That theta is called as slope. Understood? Next, there are various methods to calculate the deflections and slopes. One of the best and precise method is sorry one of the best method is an effective method is moment area method. Okay, this method is brought up it is evolved due to the various techniques and experiments and derivations. This method has been evolved. Okay, this is very effective and fast uh, solving uh, derivation, so through which we can calculate the moment area. By this moment area method, we can calculate the bending moment, the sorry deflection and the slopes. As you can see that the heading itself says that it is a moment area, right? It says it's a moment area. Means what? The area of the moment diagram is very much important in this problem, or uh, in this type of slope and deflection calculation problems. So it is very important that moment diagram is important. Without the moment diagram, you can't solve this type of problem. The heading itself says that moment area method. Okay, we'll find out in deep how this is going to be work. Okay, to calculate the slope, what we have to do is for any given beam, okay, for any given beam, we have to find the bending moment diagram of that beam. Okay, and then divide that area of the bending moment diagram. If whatever might be the bending moment diagram, if this is your bending moment diagram, right? So whatever is the area of this one triangle, okay, not two triangles, it is one triangle, take one triangle. So whatever might be the area of this triangle, okay, if suppose it is a square, okay, then divided by flexural rigidity, that is EI. This E depends upon the material. Okay, and this I depends upon the shape, right? Okay, this is the total area of the bending moment diagram. Okay, you have to calculate it. For that you have to have thorough knowledge how to you have to know that the what type of bending moment diagram is for what type of loading and what type of beam. We have studied this in the bending moment in the shear force chapter, right? So that is very much important in this chapter, and that is what a requirement is there for this chapter. Okay, and when you divide it by flexural rigidity, the area of the bending moment, once you draw the area bending moment diagram, calculate its area and divide it by flexural rigidity, that will give you the slope. Okay, and the slope is always written in radians. Whatever value you get after dividing the bending moment area diagram by flexural rigidity, it is EI. Okay, that will be in radians. Okay, that will give you the slope. Next, how to calculate the deflection? Same, you have to draw the bending moment diagram, calculate the area of the bending moment diagram of that beam, multiply with the distance, multiply with the distance of the center of gravity to the uh, point of reference. Okay, means from where you want the deflection, that point you have to take the center of gravity. If this is your beam, suppose this is your beam, right, and this is your loading, right? So what you will do, this will be your deflection, right? So deflection is here. So what, how, from where we want, from here we want, wherever is the center of gravity of the bending moment, from there to the point where you want the deflection. Okay, for this type of uh, beam, what is a bending moment? Bending moment is like this. Bending moment diagram is a triangle, right? So its center of gravity will lie where, at the 2/3 from the axis. From here it is 2/3, and from the base it is 1/3. So 1/3 into, or 2/3 into L, from where, from where you want the deflection. That distance is called center of gravity. Center of gravity distance from the point where you want the deflection, that is to be multiplied, okay, to what, to the bending moment area diagram. Okay, the area of the bending moment diagram, to that you have to multiply the distance of CG, okay, of the bending moment diagram. You have to find out the CG of that bending moment diagram, not of the beam, it is of the bending moment diagram, and this is very important. This is little bit confusing, but as you go on solving, and you as will try to derive one equation, so you will understand how you got the this formula. Okay, so then multiplying the uh, center of gravity distance from the uh, bending moment area diagram. Okay, once you multiply it, divided by flexural rigidity, EI, that will give you deflection, right? And deflection is always in mm, remember this. So if you want the deflection in mm, means your uh, the load should be Newton, okay, and your uh, the length should be in mm. Okay, that is very important. The what your dimension units are very much important. Okay, now you can see here uh, the cantilever beam with the concentrated load at the free end has been taken into consideration. Okay, and the load is provided at the free end. So deflection, where will it occur? Deflection will occur at the B point. This is your A point, this is the B point of the beam. So the deflection will occur in this point, at this point. So what is the bending moment diagram? It is a triangle. Linear line will be drawn because it is a single point load at the free end, right? So this, the length is L. To calculate the slope, what we require, we have drawn the bending moment diagram for it. For that bending moment diagram, you have to calculate the area of it. Of what? Bending moment diagram. This right? Of this you have to calculate the area. It is triangle, so half base. Base is how much? WL. This is your base. This is your height, right? So half base BL into L. So what will become? WL square by 2, right? Divided by how much? EI. So when you divide it by EI, it will become EI here. So what will be the formula for the slope? It is WL square by 2 EI. Because if you see, it is area upon EI will give you, it is the area of the bending moment diagram, right? So you get, if you divide, you will get the slope, that is theta, right? This is how you get the formula, right? Then how to calculate deflection now? Nothing, it's very easy. Same, you have calculated the area, same we have to calculate the area. Half base into height, that is your area, okay, that is WL square by 2, okay, into what? Into x, that is the center of gravity from the point where you want the deflections. So you want the deflection from where? From the B point, right? Where is your center of gravity? Somewhere here. So we want it from the where? From the axis. So what will be the distance? It will be 2/3 of L. Okay. So what you're going to do is, you're going to multiply. You can see here. You can see here. It is A into x bar upon EI, right? So A is WL square by 2, right? It is WL square by 2 into EI, that we know that it is EI, into 2 by 3 into L. So this 2 and this 2 will get cancelled. So 3 will come here and L will join here. So what will be the formula? WL cube by 3EI. Right, you can see here the formula. Same thing, nothing. We have area, that is WL square by 2, and EI at the bottom. Here also you are going to divide by EI. Don't forget, only extra is the center of gravity distance from the point where we want the deflection. The point where you want to find the deflection of that point, from that point to the center of gravity, you have to calculate the distance of the bending moment diagram. So that it is, because it is triangle and we want the area from where? From the axis, not from the base. So it is 2/3 into L. So 2 and 2 gets cancels, 3 remains. If you multiply, it becomes WL cube by 3EI. This is how you are going to calculate the formulas for every type of beam, that is for cantilever with point load, cantilever with UDL, right? Then simply supported with point load at the center, and one more is simply supported with UDL. You have to calculate the formulas for your exam point of view, because for you, for the diploma level, these are the 4 types you are going to study: the deflections and slope, how to calculate. So So same way you are going to calculate the slope and deflection for the other three types of beams. Okay, next, this is, once you derive the formulas, you will get the formulas for these different beams. As you can see, the cantilever beam with the concentrated load at the free ends, right? So it is WL square by 2EI, right? And that is your slope, and the deflection is how much? WL cube by 3EI. See, remember that your your slope will be lesser than the deflection. You can see the power here, it is always lesser than the deflection. Here also it is cube, it is raised to power 4, it is square, it is cube, it is cube, it is raised to power 4. So same way, if slope has a power of 3, means your deflection will have a power of 4. If your slope power has 2, then your deflection power will be 3. Remember this, it will be always greater with respect to deflection, right? These are the formulas for simply supported cantilever beam. It is WL cube by 6EI, then WL power 4 by 8EI, and for simply supported beams with concentrated load at the mid span, that is at the center of the span, it is WL square by 16EI, and WL square by 16EI, and WL cube by 48EI. These all formulas you have to remember, very important. Without this formula you can't calculate the problems, you can't solve the problems, so you have no choice. Otherwise you have to derive the formula at the spot as I derived it and then start solving, or you have to keep it in mind the formulas. Okay, next we'll try to solve a problem here, right? A simply supported beam of 4-meter span is carrying a UDL load, okay, UDL load of 2 kN per meter over an entire span. Find the maximum slope and maximum deflection of the beam. Take EI of a beam as 80 into 10 raised to 9 Newton per Newton mm square. Okay, it is Newton mm square. So if you want to solve, what is given? The beam is given of simply supported, it is 4 meters and UDL of, okay, how much is the UDL? It is 2 kilonewton, right? It is 2 kilonewton per meter, and E is given, EI is given, right? So what is the formula to calculate theta and Y? That is, Y is deflection, that is, that you have to remember from the table which is given and calculate by 384. It is for Y, it is 5 by 384 into WL power 4 by EI. This is the formula. And what is for theta? It is WL cube by 24 EI, right? So you have to just substitute the values and remember this. Here the important thing is, in this formula is not calculations but the units. The, if you see the problem, that it is given as 4 meters, you have to convert it in mm. Why? Because we want the values in mm here, so we have to convert it into mm because we want the final values in mm. So we are going to convert the 4 meter into 4 mm, 4000 mm. So once you convert one unit into one unit, that is in mm, then other should also be in mm. So what it is, 1 kilonewton per meter is equal to 1 Newton mm. It is kilonewton per meter will be is equal to Newton per mm. So if it is 1 kilonewton per meter means 1 Newton per mm. Same way here it is given as 2 kilonewton per meter, so we want in mm, so it becomes, when you uh, calculate in mm, change the units, you will get it is same as 2 Newton per mm. So this is given, right? It is given already in mm, so no worry. So just substitute the values in the slope formula. You will get as 0.02 radians, and if you substitute the values, same values, nothing value, the rest power value will change. That will give the value as 83.33, right? If you, this is what is 83.33 mm is the deflection, maximum deflection. It is not a permissible deflection what we want. That is, this is what is asked in the problem, that what is a maximum deflection, right? Maximum deflection is nothing but what by loading this much of load, UDL load, what will be the maximum deflection it will occur. But we can't uh, we have to first find out what is the permissible limit as per the Indian standards, what deflections we can allow on the beam of 4 meter of span. If you calculate it, that is 4000 divided by 325, it will come up near to, it will come near to 12.30 mm, because we have taken this value in mm, so this will come in mm. So the deflection of the beam cannot be more than 12.3 mm in actual considerations. They have said here to find out the maximum. No worry, the answer is correct. But in the actual cases, we can't allow the beam to deflect more than 12.3 mm. That is what it says, that you can't allow the deflection to be more than 12 mm. Okay, that is what it is saying, that the permissible limits you have to calculate. Okay, this is how you're going to this is all about your slope and deflections. If you understand the derivation concepts, it's very easy to derive the formula and start solving, because what happens is remembering so many formulas in the strength of materials is very difficult task, because there are a lot of number of uh, formulas to be remembered. If you are able to solve the derivations, you can just but you have to know the bending moment diagrams. That is very much important. And the how to calculate the center of gravity of different uh, a shapes of the uh, bending moment, that is parabola, triangular, okay, then rectangular. It is for parabola, it is 3 by 2. It is how it is 2 by 3, here it is 3 by 2. That you have to remember in parabola case. Okay, if suppose this is your beam, cantilever beam, right? So what will be your the cantilever bending moment diagram? It will be like this, right? I will draw it once more. So this is what is your bending moment diagrams, right? So what will be your area? It will be 3 by 2. Okay, it is because it is curved, so it will be 3 by 2 into WL. It will be, what will be here? Because it will be WL square, right? It will be WL square, right? By 2 it will be. So the base will be what? WL square by 2. Okay, so you have to multiply it by EI. So how much it will become? 4 square by 4 EI. It will be like this. You should be able to solve the derivation so that you can find out the values, formulas.